Hi everybody! So in today's video I'm going to be introducing the idea of what's called a related rates problem in calculus. And here's the basic idea. In the real world, there are times when multiple variables in a situation are all changing with respect to time. So if you imagine, for number one, that you are inflating a balloon, and we think about what might be changing while the balloon is being inflated. So let's imagine we have a balloon, and it starts off pretty small, and we're going to blow air into that balloon. As we add air to the balloon is going to get bigger and bigger and bigger. Now, as this is happening, there are several different things that are changing. The radius of the balloon is changing. The volume of the balloon is changing. The surface area of the balloon is changing. And all of those things are changing at different rates as you blow more air into the balloon, so over time. We can do the same thing where we imagine a cylindrical cup that's being filled with water. So if you imagine that you have a cup that's shaped like a cylinder, and we're going to fill this cup with water. So as we add water to the cup, so maybe the water starts off down here, and then we add more water to the cup, and then the water is right here, and it fills it all the way up to here. And then we add more water to the cup, and then maybe the water is filled up to here. As we do that, there are several things that are changing. The height of the water is changing. The volume of the water is changing. But what's not changing here is the radius of the water. So if you imagine the radius is here, the radius of the cup is not changing. So that's important to note, is that there are some things that are not changing as we fill this up with water, and that's going to be important in some of our future problems. Now, anytime we're looking at a rate of change or how fast something is changing, we're going to be finding the derivative. That's kind of what a derivative tells us, is the rate of change. So when we have these types of problems and we have these relationships and formulas that describe what's happening, for example, if you don't remember, this is the area of a circle is pi r squared, and this is the Pythagorean theorem, the distance squared equals x squared plus y squared. When we have these types of formulas that tell us about the relationships between these variables that are related, we're going to be taking the derivative of these problems with respect to time. So here's how we do that. So if we want to take the derivative with respect to time of the equation area equals pi r squared, then the derivative of area, the a, with respect to time, would be dA over dt, the derivative of area with respect to time. And since pi is just a number, I'm just going to treat it like a number. So all I'm going to do for the pi r squared is I'm going to drop the 2, leave the pi, leave the r, and decrease the power by 1. So there'd be a little invisible power there, which is the power rule. But then, because I'm taking the derivative with respect to time, I'm going to multiply by dr over dt, because that would be like kind of using implicit differentiation. When you did the derivative of y, you wrote dy over dx. Well, now we're going to write dr over dt because the radius is also changing with respect to time. So what makes taking these derivatives different than taking our derivatives before is that now, since every variable is changing with respect to time, every time you take a derivative, you need to put dA over dt or dr over dt. It can't ever just be 2 pi r. You have to attach that to show that it's changing with respect to time. So another example, if you wanted to take the derivative of this equation with respect to time, let's start with the d. So you would drop the 2, you'd have 2d times dd over dt, the derivative with respect to time, because that's kind of like the chain rule. You're doing implicit differentiation with respect to time. You're attaching it like the chain rule. Then you would do the derivative of x squared. And x squared's derivative would be 2x times dx over dt, the derivative with respect to time, because everything is changing here, the radius, the height, the volume, the everything. Finally, you would do the derivative of y squared, and the derivative of y squared would be 2y times dy dt, the derivative with respect to time. Let's go ahead and look at taking some more derivatives with respect to time. So if I give you this volume formula, which happens to be the volume of a sphere, and I ask you to take the derivative with respect to time because the volume and the radius are both changing, just like in our balloon, the volume and the radius were both changing. Since the volume and the radius are both changing with respect to time, when we take this derivative, we're going to use this technique where we attach these rates because everything is changing. So the derivative of volume would be dv over dt. And then to take the derivative of 4/3 pi r cubed, we just drop the 3. 3 times 4/3 is just 4 pi r squared. So we decrease the power by 1. And then we multiply by dr over dt because everything here is changing with respect to time. So to show that the radius is also changing, we multiply by dr over dt. Next, we're going to take the derivative of sine of theta, which is equal to y over d. So if you think back to when we learned how to take the derivative of sine, the derivative of sine would be cosine of theta times, now we need to do the derivative of theta, so d theta over dt, which is changing with respect to time. And that's going to be equal to, for the other side of the equation, we need to use quotient rule. So low d high, so the derivative of y would be dy over dt minus high, which would be y, d low, so we would take the derivative of the denominator, which is dd over dt, and low squared, so the derivative of the denominator, sorry, not the derivative, just the regular denominator, squared, goes down below. So the big change here is that when you have rates that are related to time, we need to make sure that every variable gets its own derivative rate when we take the derivative so that we can represent that it's changing with respect to time. Other than that, all of our derivative rules are the same. We still need to know quotient rule, we still need to know our trig rules, we still need to know power rule. The only real big difference here when we're taking these derivatives is that we need to attach these little chains to show that everything is changing with respect to time. Okay, thank you guys so much for watching. We're going to practice finding some derivatives in class. See you then.